Eigenvalues and Eigenvectors. This section here gives an introduction to the subject. We want to be able to find the so-called eigenvalue, eigenvector to a system that corresponds to A. There are many uses of this. I think the main application of the eigenvalue, eigenvector is to the solution of a differential equation. Those solutions to a differential equation, where the differential equation is set to be, it could be homogeneous or it could be non-homogeneous. It's a linear system with constant coefficients. I don't know if you recall that, with the constant coefficients where you get the terms are exponential in order. You get some e to the mx, whatever. All those values for those numbers m, they're actually the eigenvalues. And then when you actually write the solution out, the solution itself is said to be the eigenvector. And so there's one really neat way of solving the differential equation is really just finding the eigenvalues and eigenvectors. And from there, there's a format in terms of how you take the eigenvalues and plug them into the form for the solution for the differential equation. It's the same thing. So actually, you have a differential equation, and you got two ways you can do it. You can solve the method that's given in the typical textbook for differential equations, or you can use linear algebra and find the eigenvalues, eigenvectors. You get the same thing. The applications of the eigenvalues and eigenvectors are many. There's something called a dynamical system, and the solutions for the so-called dynamical system are said to consist of the eigenvectors. But right now, we just look at what is an eigenvalue, what is an eigenvector. If A is a square n by n matrix, then a vector x that is said to be an element of Rn is called an eigenvector of A if Ax, capital A, the matrix A times x, is a scalar multiple of x. That is, the system Ax equals to lambda x for some scalar lambda. Lambda here is called the eigenvalue of the system. And here's what they're saying. It's kind of fuzzy when you look at the language. They're saying, take a matrix A that is perfectly fine and break it. What I mean by break it, take a matrix that has real solutions, a unique solution, and now make its solution of the form infinitely many. We break it. We break it in the sense that we take a matrix and we find a scalar multiple of it. Well, a scalar multiple is said to be, watch this, linearly dependent and not linearly independent. So we take a linearly independent set and we force it by trying to find some lambda, which is this eigenvalue, and we make it linearly dependent. Now, why is that? Now, here's the reason for that. What they're saying is, you got this matrix A. I want to take a copy of this matrix A, put it in a different form, a different format I can use for neat applications out there in the world. Wow. So here we say, and as a matter of fact, I don't know if you all recall in Calculus 3, talk about you want to solve an optimization problem, find the maximum value on some type of big squiggly surface or whatever you have. And we said that there's one way you can do that by using Lagrange multipliers. You remember that? Lagrange multipliers, where the Lagrange multiplier is some lambda itself. It's a scalar multiple. It's really the same idea. You kind of, what's the use of this process? Well, that's what happens when you go and get the flu vaccine, right? They take a broke down version of that disease and they infiltrate it in your body. And your immune system, which is stronger, eats it up, but it recognizes it. So if it comes back again, your body has the immune capability of fighting it off later on. You take something, you break it, right? But you use that brokenness, to fix something up back over again. Wow, boy, that's a sermon. But anyway, I don't have time for all that. Okay, hold me back. Okay, so the characteristic equation, if A, man, this is a lively bunch, I tell you, man. Bless your hearts. Okay. If A is an n by n matrix, this theorem here, then lambda is said to be the eigenvalue of A if and only if it satisfies this equation, which is called the characteristic equation. Now, where does this equation come from? Let me see if I can just write it down real quick for you. It comes from the setup, from the definition. All theorems come from definitions. So, it's weird. So, we say that lambda times x is a scalar multiple of A times x. So if that be the case, we have AX is equal to, and because I'm left-handed, I write my lambdas backwards. So you'll know later on. What is that? So, well, take one to do that. Lambda times x. This implies, what I'm going to do is get the AX on the right side. So here I have 0 is equal to lambda x minus AX. Now, if you will, just turn that around. Just say this is lambda x minus AX equal to 0. Now what I want to do here is to do right multiplication of x. So this is lambda times the identity minus A times x is equal to 0. I take the determinant, set it equal to 0. Remember we said that if the determinant is equal to 0, doesn't that give you linearly dependent? Right? Linearly dependence. Like I told you, we're taking something, we're breaking it, but we're going to use this broken form to do something really neat and to be really strong for other rich applications out there. Okay? So now what we do here is take the determinant of both sides, yields determinant of lambda times identity minus A is equal to 0, which is what that is, and that's the characteristic equation. When you solve for this determinant, we get the eigenvalues. You take each eigenvalue and plug it back into this, the form of lambda I minus A, and we get the eigenvectors. Let me show you. You collect all the eigenvectors, and those vectors form a basis for what we call the eigenspace. Now, eigen is just a German word for characteristic, right? Some particular strand in a multiplicity of many. And here we say, I take one of them, and I call this guy a characteristic of everything in that particular span. So the problems here: find the characteristic equation for the matrix, find the eigenvalues for the matrix, find the eigenvectors, and then find a basis for the eigenspace for the matrices. And I say matrices, I think I got number 2 down there as well. Okay, so part A. So we want to find this is lambda times the identity minus A. This is lambda times, this is a 3 by 3, so this is 1, 0, 0, 0, 1, 0, 0, 0, 1. That's lambda times the identity minus A, 4, 0, 1, negative 2, 1, 0, negative 2, 0, 1. This is lambda 0, 0, 0, lambda 0, 0, 0, lambda minus 4, 0, 1, negative 2, 1, 0, negative 2, 0, 1. So here we end up with lambda minus 4, 0, negative 1, 2, lambda minus 1, 0, positive 2, 0, lambda minus 1. That little negative right there, you got to be careful with that, right? So it's minus all those terms in this matrix A. Now I look at the determinant. The determinant, I can just write this, lambda minus 4, 0, negative 1, 2, lambda minus 1, 0, 2, 0, lambda minus 1. I use cofactor expansion. Here I expand along the first row, lambda minus 4, times the matrix, the determinant of the submatrix found by deleting the first row, first column. This is lambda minus 1 times lambda minus 1 minus 0. So this is lambda minus 1 to be squared. Then I come to the negative 1, delete its row and column. I have left 2 times 0, which is 0, minus 2, it's a negative, times lambda minus 1. That's set to equal to 0. Set to equal to 0 because we're looking at the characteristic equation. So we simplify that. I could factor out lambda minus 1 from everything. So this is lambda minus 4 times lambda minus 1 plus 2. That's equal to lambda minus 1 times lambda squared minus 5 lambda plus, this is 4 plus 2 is plus 6. Can factor, if you please, lambda minus 2 times lambda minus 3 equal to 0. So the characteristic equation is this guy. Part B, find the eigen values. You set the equation equal to 0. That implies that lambda equals to 1, lambda equals to 2, lambda equals to 3 are our eigen values. There's a bit more to get the eigenvectors. So for the eigenvectors, first let lambda equal to 1. This implies I go back to the matrix for lambda times the identity minus A. I go to this guy, not the determinant. So lambda is 1. I plug in a 1 here. So that's 1 minus 4. Get negative 3, 0, negative 1. 2, lambda is 1. 1 minus 1 is 0. You get 0, 2, 0, and 0. Reduce this guy. Reduce it. Row echelon form. Reduce that on your calculator. And you get 1, 0, 0, 0, 0, 1, 0, 0, 0. Now the work begins. So I take this guy, and this implies here that x sub 3 is equal to t, x sub 1 is equal to 0. Excuse me, this is x sub 3 is equal to 1. equal to 0. 1 times x sub 3 is equal to 0, so x sub 3 is equal to 0, excuse me there. X sub 2. See, if you write this guy in what it ought to be, this is 1 0 0 0 0 0 0 0 1. So I have a 1 on the diagonal for A11 and A33. But I have a 0 there at A22. So that's that x sub 2. So x sub 2 is equal to t. This implies that the eigenvector would be x sub 1 is 0, x sub 2 is 1, x sub 3 is 0. There should be an eigenvector that corresponds to the eigenvalue. So I have to look at the next one. Let lambda equal to 2, because I have lambda equal to 1, lambda equal to 2, lambda equal to 3. So let lambda equal to 2. And this implies that 2 times the identity minus a gives us, I plug in 2 for lambda, I get 2 minus 4, negative 2, 0, negative 1, 2. 2 minus 1 is 1, 0, 2, 0, and 1. Reduce this on your graphing calculator. Now rows 1 and rows 3 are multiples, so row 3 goes out. This becomes 1, 0, 1/2. Reduce this guy. That's 0, 1, negative 1. You put it right in your graphing calculator, it comes out 0, 1, 1. And you look at that, this tells me that x sub 3 is equal to t. X sub 1, make sure I didn't get it. This is 2. It's a negative 1. This is negative 1 on my calculator. So x sub 1 is equal to negative 1/2 t. X sub 2 is equal to t. So it's corresponding, I'm putting a hat on it to let that be denoted as the eigenvector. X sub 2 hat is equal to x sub 1 is negative 1/2. X sub 2 is 1. X sub 3 is 1. And that's, times t, but you just need the values here. And then, for that third one, let lambda equal to 3. This implies that 3 times the identity minus a is equal to, plug in 3 for lambda, it's up above, and it gives you negative 1, 0, negative 1, 2, 2, 0, 2, 0, 2. Reduce this, we get 1, 0, 1, 0, 1, negative 1, 0, 0, 0. And this implies x sub 3 is t, x sub 1 is negative t, x sub 2 is equal to 1 times t. So x sub 3 hat, its eigenvector, is x sub 1 is negative 1, x sub 2 is 1, x sub 3 is 1. It's times t, but Just look at the numbers there. Now part D, it says find the basis for the eigenspace. Find the basis for the eigenspace. The eigenspace consists of no more than just the vectors from the eigenvectors. That's all that is. So here, it's the first one, the second one, the third one. The first one was 0, 1, 0. The next one we got was negative 1/2, 1, 1. And the third one we got was negative 1, 1, and 1. Make sure that's right. Yes. Now, number 2. Number 2 is pretty decent. Try your hand at that. I don't have time to work it. But the problem on the test will look like the number 1. Okay? Is way more straightforward than this guy. Number 2 here, you have to do a lot of work to get the characteristic equation to work out for you. It's nothing but algebra. But the problem on the test will look like the number 1. Very straightforward how I got the eigenvalues. Lambda minus 1 times lambda minus 2 times lambda minus 3. Very easy like that. The other way, this problem, you have to use synthetic division to get those eigenvalues. So let me turn this off and then let me talk to you for a couple of minutes.